those are up conversion. So how do you actually, enhance more emission over here for that application, or more emission over here? And this is where you need to understand the physics. And so there is a lot of what we call nanoscale control of how the excited energy can make it flow in different channels and emit. So that depends, and again, since most of you, there is no physicist here, is there? Okay, so we will just talk about, in general, that depends on, firstly, what kind of crystal phase you may have of the nanoparticle. So the same nanomaterial can exist in more than one crystalline phase. And so you want to choose the right phase that gives you maximum emission, maybe emission in certain channel. Then you want to have a lattice of that crystal that does certain kind of, energy on the surface of, because surface generally can also deactivate. So a lot of energy can be lost from the surface in there. So you want to make sure that these things are, by understanding the physics, and I wrote in a review called Account of Chemical Research, you can enhance maximum emission or emission through selective channel. Okay? So here gives an example that if you take the erbium in the same sodium yttrium 980, that turns IR, because the dyes are very strong, they could be very strong, right? So they can transfer energy in many steps to enhance the emission over here. And we showed that this upconverted emission is so much enhanced. Without this dye, if the emission is very weak emission, this upconversion at 800 in thulium. But when you do this way, is 100 times enhanced. Okay? Very strong, that you can even use a low power lamp. You don't even need a laser. A lamp at 980, in this case is 800 nanometers, and it can be upconverted very strongly. Okay? So we showed that this energy transfer process, so these dyes act like antenna. They're antenna, they absorb light and they funnel the energy into the core where you can emit light. Okay? So then this is an example of core shell structure. Now again, as I said, in nano formulation, the excited state light, excited state can emit strongly if you want imaging. You can do photochemistry, you can do heat generation by looking at nanoscale manipulation. Okay? So do physical characterization. So you have made the material, right? And you want to look at their size. So how do we determine EM, transmission electron microscope? With that you can actually see the size and the shape together. A first one, and you can get information on the size. That's called hydrodynamic radius. Effective radius of nanoparticle dispersed as a colloid, dynamic light spectrum. Or you can do AFM of the sample, dried sample. So these are, and if it is crystalline, what kind of crystal phase it has. Like I showed to you in case of erbium, that it could be hexagonal or cubic. So you want to determine, and for that you do X-ray diffraction or high resolution transmission electron microscope. Okay? Uniform nanoparticles, so they have a large size variation, light scattering. And all of a sudden you see the sizes are not 50 nanometers that I saw in transmission electron microscope, but those have aggregated. They have made a bigger sound, that aggregation, and they're more dispersed. So this is the first step you want to do, is when you make the material, you have done elemental analysis to confirm that those atoms are there, that is the right kind of material you have. Then you want to do the size, shape, whether they are crystalline, so that they can all be very similar, and then whether they're aggregated in dispersion. I want to make sure all these. So let's look at some examples of imaging and diagnostic, and then after that, my goal is that we can run through imaging faster, and then we will get on sensing, and we will get to therapy, because a lot of you are interested in how do we apply to therapy. Okay? Many different kind of imaging. A nanoparticle allows you to do that. An optical probe, either you can use organic dye filled in a nanoparticle, you can use quantum dots, that up-converting nanoparticles I talked about. You can also use metallic nanoparticles because they absorb strongly, and they also scatter light strongly. So if you use a scattering, it's called, then you can do dark field imaging, contrast versus the background, because the light is scattered, so those things are. So how do we do that? Well, you can either take, when you make nanoparticles, you can put a dye in there, and the dye, if it is hydrophobic, it can get inside the hydrophobic part of the nanoparticle. When you are forming, it will include the dye in there. That's called preloading. And it's as you are forming, the nanoparticle getting in there. Or the nanoparticle may be mixed with the material, like polymeric material, and they are uniformly distributed, and you have nanoparticle, okay? Or you can have a porous nanoparticle, like silica, mesoporous, and you can post-load it. You can fill dyes in the pores, okay? So there are many ways, and the same principle goes for drugs, how you encapsulate. However, the dyes, most dyes have this property that if you load them in high concentration, because you want to make them brighter and more emissive, their emission is quenched. That's called concentration quenching. Or higher concentration, the dyes, when they come together, they decide not to emit but go as a heat. So concentration quenching, you want to avoid that. So what do you do then? Then you want to kind of use a low concentration of dye so that they are not aggregated, they are dispersed. But if you use a low concentration and you want to do 2-photon imaging, which is a weaker process, we calculated by quantum simulation that in this case the rattling angle can be 74 degrees, but in this case is only 38. Okay, limited. Okay? So in this case they are much more emissive. So if you use high concentration of this, or even pure dye nanoparticle, unique dyes are very narrow. They are like 10 nanometers wide. So you can use different particles and color label them. That's what is called. Then we found that again, if you put a shell over this, then it's much more emissive because it protects the surface from deactivation. So that's why if we use cadmium selenide, let's say, we will put a shell of zinc selenide. Light is emitted here will not be absorbed by the shell. It comes out. Okay? And the cell's function is to protect it. Then we put a layer of organic like lysine, which is amino acid, to make it dispersible in water. Okay. Then on the surface, we put these antibodies, remember, with a lock that grabs onto antigen on the surface to attach and get in there. And then in addition to that, you put this pegylation group, which is polyethylene glycol, very often abbreviated as PEG. You attach that because that one enhances the circulation of nanoparticle in blood so that it has more time to find where it's supposed to be by this targeting group. So this is the kind of nano formulation you use for imaging if you want to do that. But the same strategy you can use for drug delivery if over here the drug, okay? So this is a pancreatic cancer cell line where we use a quantum rods, again a longer one, which has emission little shifted towards red, and the quantum, we do a lot of this investigation, particularly in the blood-brain barrier. We simulate the blood-brain barrier. That's what we call phantom model. And then we can see, first step is whether these tagged nanoparticle and an emitter, they are crossing, and we can detect by fluorescence on the top, right? And then we can monitor, as we showed to you, the injecting in the tail vein, monitoring emission in course of time, how the nanoparticle migrates through the body to get to the target, which is the tumor. So that's what is called biodistribution. And for your nanoparticle, and modify it, how? Chemical makeup, size, charge, surface coating, all these manipulate so that you can get quickly through the delivery route, it crosses biological barrier, it has favorable biodistribution, near the cancer site, tumor tissues, the normal, okay, but it's doing this. Second one is field directed. So suppose you put in the nanoparticle some magnetic nanobead together. And now you can take a magnet and drag it, a nanoparticle, to the tumor. That's called magnetophoretic. At the site where, that's the beauty of, that you want to use it for this, using multimodal carrier, you want to